Hello and Assalamualaikum. The objective of the journal that I chose for this assignment is to study and evaluate the effects of defects on the thermal properties of zirconium diboride and its hexagonal lattice structure. Zirconium diboride is an ultra-high temperature ceramic that has a melting point of 3000 to 3245 Celsius and are widely known for its application that requires high thermal tolerance, such as nuclear reactors, turbine engines, and aircraft. As shown here is the hexagonal honeycomb lattice structure, which is the structure of zirconium diboride. Because zirconium diboride are widely used for the internal design of nuclear reactors, it should be evaluated carefully on its life cycle potential based on expansivity, which is the amount of a material expand and contract per unit length due to 1 degree of change in temperature. It stated that the study has shown that the thermal expansion of zirconium diboride is anisotropic, which means that it has a different thermal expansion property along the various lattice directions. Because of its anisotropic properties, it has varying bond strengths that determine the stiffness, thus the expansion of the material.
Surface oxide, metallic impurities and carbides are the defects that are inevitably created throughout the processing stage or it existed in nature. These defects will cause microscopic structural change that will lead to redistribution of localized electron density. But the perfect crystal of zirconium diboride rarely exists due to its partially covalent nature and induced defects from synthesis and sintering process. There are many methods used in this research in order to evaluate the data from the available numerical and experimental data. The temperature dependency and the anisotropic nature of the material for coefficient of thermal expansion were evaluated with perfect and other impurities configuration. The molecular dynamic simulation were conducted using large-scale atomic or molecular massively parallel simulator or LAMPS.
This figure shows the graph of coefficient of thermal expansion per unit Kelvin versus the temperature. And it shows 5 different types of zirconium diboride, 4 with impurities and 1 which is a perfect zirconium diboride. When the temperature was 3000 to 1200 Kelvin, all the configuration shows a stable amount of thermal expansion, and all the configuration peaked when the temperature reached around 1500 Kelvin. After 2000 Kelvin, which is approaching the melting value, all the configuration will undergo contraction. But when the temperature reaches the melting range of zirconium diboride, which is around 2900 Celsius to 3000 Celsius, which is around above 3000 Kelvin, it shows a gradual breakdown because the structure has expanded uncontrollably. The configuration that stood out the most is the hafnium configuration because its coefficient of thermal expansion, which is the color of red, shows that this configuration has a higher rate of expansion when compared to the other configuration, because when it undergoes contraction, the amount that it suffers is very little compared to the other configuration. The second figure shows a graph of different expansion for different axes because of its anisotropic nature. The color of red represents the x-axis for hafnium and boron impurities. Blue represents the z-axis for hafnium and boron impurities, and finally, for the green with a diamond, it represents z-axis for carbon impurity, and green with with a circle represent the x-axis for the carbon impurity. The graph shows that the x-axis for all the configuration undergoes a uniform and slow contraction, while the z-axis shows a gradual expansion. To further understand the effects of impurities on the structural characteristics, a graph of density of state was plotted.
This graph shows the density of state for the perfect zirconium diboride and its projected density of state, which is PDOS, and total density of state, TDOS. The number of states for the perfect zirconium diboride reduced with increasing energy level. The DOS for the covalently bonding impurities are closely overlapped with the pure crystal, but with more dominating states likely from the projected orbital of silicon and carbon at higher energy. The potential bonding interaction between the covalent nature of zirconium diboride with both silicon and carbon is noticeable in the overlap, which is not the same for the metallic impurities. Both carbon and silicon have an almost similar graph but with a different value. The metallic impurities show states dominating at lower energy. As seen from the graph, both hafnium and tungsten started at a negative value compared to the others, which started with a positive value and slowly increased.
The first graph is for the perfect zirconium diboride. The result shows a good dynamic stability because there are no imaginary modes, and such stability is expected for structures with high atomic defect energy and low tendencies for atomic explosion. This graph shows zirconium diboride with impurities which is carbon, silicon, hafnium, and tungsten. The carbon and silicon impurities shows dynamical stability similar to the perfect structure, but in addition to the dominant acoustic mode, there exists more low frequency optic modes, which is hafnium and tungsten, as seen in the graph, where both hafnium and tungsten have low frequency compared to carbon and silicon. The added optic modes for silicon are at relatively higher frequency than carbon, as seen in the graph. For metallic impurities, negative phonon, which is the imaginary branches, demonstrate the dynamic instability for both configurations. The development of near zero frequency phonon transmitting between normal and imaginary modes indicates changes in charge density area, showing that both metallic impurities have severely affected zirconium diboride initial charge density distribution.
The next graph shows the computed specific heat plotted for each respective impurity. The specific heat reached a hard limit near the dBi, which is a unit to express electric dipole moments of molecules, at the temperature around 750 Kelvin. The presence of 5% volume of hafnium and tungsten impurity shows decreased specific heat capacity, which is around 158 joules per mole per Kelvin at reference 750 Kelvin temperature. The value is significantly lower than calculated for carbon and silicon impurities. When the lattice vibration reaches its maximum, phonon contribution will not increase even with temperature based on the Debye model. The phonopy applies quasi-harmonic approximations QHA, which is not applicable at very high temperature of complete anharmonicity. Hence, this study specific capacity in the temperature range of 0 to 1000 Kelvin has been investigated. This shows the change in the thermodynamic properties with respect to lattice temperature. The initial energy change in the material are clearly observed in entropy dispersed. It is non-trivial but shows differences in the microstate, which is the degree of freedom of the various material. Translating it by equipartition theorem, the small offset in heat capacity values, which is in the graph, is equivalent to change in its degrees of freedom. The overlaps further align with the differences in the phonon bands between the covalent, which is carbon and silicon, and the metallic impurities, which is hafnium and tungsten.
In conclusion, the analysis development of structural differentiation in zirconium telluride and other metal hydride is supported since the manufacturing process has shown wide variation in density and purity level of the material. The information about the effects of impurity has been gathered so that a better understanding can be achieved for better forecasting of thermal properties of zirconium telluride-based material. And it has been shown that the volumetric coefficient of thermal expansion is determined by the anisotropic z-direction, and the exponential rise of the coefficient of thermal expansion towards melting temperature will result in a structural breakdown.